Okay, so of course last time we just finished up talking about the array index list. Actually, no, that's not true. We just finished up talking about the unordered list. And we were just starting the array index list. And the array index list had a lot more stuff going on. We had an add, set, get, index of, remove. And I could have added a whole bunch more things. I could add whatever I want. But then we also saw that funny thing at the bottom. That T, ampersand, operator, square brackets, int I. Which looks new, right? This is definitely new to us. We haven't seen this yet. I mean, it looks just like a function, but it's going to be special. We'll see in a moment. Take note of the return type of that. What's that return type? No. T ampersand. Okay, what does that mean? T reference. Good. But not a pointer, reference. More on that in a moment. So, our constructors, we're going to be lazy again and just pass the information right on to the base class's constructor because there's nothing extra fancy to add here. So let's look at this add. Well, I mean, it's not overly crazy. What does this add do? Well, it looks like this add is going to take an index and we're going to insert the element at a given index. Now let's assume we don't want to just override whatever is in that index already. We're going to have to move it down so there's space for it. So if I have something already in index 5, and I don't want to get rid of it, I'm going to have to move the thing in index 5 to index 6 and everything down in order to make room in index 5 for the new element I want to add. So what is it saying to do? Well, if we have to expand capacity, expand capacity. Otherwise, shift all the things up starting at index to the end. Although actually when we looked at shift up, we actually know it started at the end and moved towards the index, but anyways. Then we set the list at location index to element and increase the size. Nothing crazy. All those simple little steps, that's it. Any questions about this? If I didn't explain this, how it was supposed to work, you should be able to, at this stage, look at this code and go, oh yeah, okay, I know what it's doing. A big thing, especially at this stage of computer science, especially when we get to tests and whatnot, like on the final exam, there's 3 styles of questions I like to have. Sometimes I'll say, here's the input, here's the function, and I'll ask you, what's the output? Right? If you know this is the input, you know we have a function that takes some input, what should I expect to see at the end? Sometimes I'll ask questions that are like, here's the input, here's the output, what's the function? Here's what I give you, here's what I want in return, what should the function look like to do that? And sometimes I like to do the inverse thing, which is here's the output, here's the function, what would the input have had to have been? Now in this case, if I just said, well, okay, explain this function, that's almost even like a simpler version of that. Like, what does this code do? Well, and we're going to add something, and I guess it's going to add the thing at index I, it's going to have to make room, input the thing, size plus plus. Nothing crazy. Here, I guess if we're just saying add element, where are we putting this if we call this add? End of the list? How do you know? Because that's what it says. So the list at location, whatever size is, becomes the element, increase size. This is kind of like, it's going to be very similar like the push, right, that we saw with the stacks. Any questions about this one, or are we okay? I mean, this is an even simpler version. What do we, oh, we've got set. Set a given thing at an index to an element. What is that check doing? What's that if statement asking?
Making sure it's in the actual range of indexes that exist.
Right. It's not going to let me say, change the thing at index -7 to this. Because it should say, well, I mean, that's impossible. That's not a thing. So this is just some information validation code to make sure it looks good, that it can actually work. So that's handy. Maybe it's a good idea to include something like that in our code. Otherwise, take the list at that index and set it to the element. This one will overwrite whatever's in that index already. Which is fine, I guess, because that's what this function's supposed to do. Just set it. If we don't want to overwrite it and you want to insert something, well, we probably want add, not set. And get, well, similar check, but this one's just going to return the thing at that index. That's all it is. It's basically like a getter and a setter, kind of, right? But it's a getter and setter for things at a specific index in our indexed list. So far, so good, right? Any questions at all? This, well, this is similar to the other ones that we saw. Index of a given element, well, find it. If it's -1, that means what? If you remember what find did.
It does not exist in your list.
It doesn't exist. Underscore find will do a linear search. If it finds something, it'll return the index of that thing. If it doesn't find anything, it just returns -1. And I guess -1 for us is like a special value that we know that if we ever see that value come back from that function, that tells me that must not have existed. So here we just call find, and we basically relay the result back. But I guess actually it's even simpler than that. No, it's not simpler than that. It's just that. I mean, here I guess if it doesn't exist, it throws an exception. I could have just had it return -1, I guess. But then again, at the same time, if you're a programmer in the future, how could I possibly know what you want to do if you don't find the thing in that list? Do you want to just carry on? Do you want to crash? I don't know. That's up for you to decide. So I throw an exception if I don't find it. Did I have to do that? No, not really. But I just did it that way. Remove. Well, I guess remove something at a given index. Check if it's valid. Get the thing at that index. Shift down. Reduce the size. Return the element. That's all. I guess this remove also returns the value of whatever that thing was. Okay. Now this is a little funny. Have a look at this. Take a second and really look at this code. It's actually, there's not a lot of code. It's rather straightforward. But take a second and look at this and take very special care to pay attention to what the return type is. Give yourself a minute, talk amongst yourselves. See if, even though I haven't explained this to you yet, give yourself a minute, think, talk amongst yourselves to see if you can actually kind of conclude what it must be doing based on what you already know. Go, chat. All right, what do we think? Ignore what I drew for a second. What do you think?
Well, it's going to tell you what's in the list unless it's outside of the list, like it's smaller than the elements or bigger than the elements.
And you're not wrong, but I was looking for a little more of a little deeper of an answer. Does anyone have a thought? No, it's a little bit of a mystery, huh? Oh, yeah, what do you think?
So you define an integer I and what it is doing. You define the operator as well as the square brackets. And what that means is that, so the if statement basically covers so that if the I is less than 0, which would mean that it's lower than the lowest.
Let's not worry about the if statement. Let's just focus on the return.
Okay. returns, so this is referring to the actual implementation of the indexed list, and list at I would basically be if the user is using the operand of the square brackets, it will return what would be at that set index that we defined.
Again, you're not wrong, but I'm going to add a little bit to this. What's the return type? T reference. First we gotta remember what is that reference. If we've got just a value like this, int a, at the back, can you see that reasonably well? Int a, what's in the box? It's a box. If we have an integer pointer b, what's in the box? Well, it's a pointer to that. Let's do my set. Okay? So that's what we've got. But when I have a reference, it's like, it's not a pointer. It's like another name. It's a way to get something and have it be like another name for that exact same thing. So I am getting, effectively, this box. Not the 5, I'm getting like the box. So this is important because I've got an array. And I've got some value in there, I don't know, it's a little person. It's type T, whatever. When I return, let's say that happens to be index I. I don't know what I is, it's arbitrary, it doesn't really matter. I'm not returning that person. I'm returning like the box. And when I have access to the box, it allows me to look inside the box, but also change what's inside the box. Where if I'm only returning the person, that just gives me access to that person. But I wanted access to like the box. The reason this is important, oh yeah.
Would it be like returning the address?
Kind of, but no, absolutely not at the same time, because the address would be like the pointer. So it's not, you're not literally returning the box, but it's kind of a nice way to think about it. The reason this is important is, let's say I add a couple things to my list. So have a look at this code, nothing crazy. I've just got an integer list, and I'm adding 5, 4, 6, 5 to it. Why? Because. Now I can actually do stuff like this. So one, I'm dereferencing my list because it's a pointer. But I can actually, one, access the thing at location 3. If I hit run, what should the first line of code what should the first line printed out be? 5. Why? Well, because it's the thing at index 3. But then, what is that last line of code doing? It changes the 5, the thing at location 3, index 3, to 44. If all it did, if that code didn't return like the box, but return the person, that printing out would kind of be fine because it gives it for me. But the last line there wouldn't really make sense because I'm trying to change what's in that box. Take a second, think about it. Think if you have any questions about this. You could go your whole life not doing this. It doesn't matter. But now I can access my list object that I've defined kind of like an array with the square brackets. In fact, you can access this list, this index list, in a way that it's going to be basically exactly like how it works in Python, right? The lists in Python. Because the lists in Python, you could access information with the square brackets. Well, now we can do that here, yeah.
Why would you do that over like get or set? Is it just easier?
It's just easier. It's a nice convention. For decades, we've been accessing arrays, contiguous linear things with these square brackets. So now we can do it with this new linear thing we've got here. Yeah?
In the actual, from the last slide, in the
like right here. Or oh. You mean right here?
Yeah, yeah. Is that just convention for that, or do they need to be there?
They need to be, so that's saying like operator, square brackets. Now imagine for a second I could come in and write like operator less than or something. Suddenly I can start to define what it might mean for one thing to be less than another thing, or greater than or equal to. Maybe addition. Maybe I can actually define what it means to someone use for someone to use the plus operator on type lists. If we wanted it to act like Python, what would I want that to do? Who remembers? What happens when you add two lists together in Python?
The second list gets extended to the first list?
Yeah, it's concatenated, appended, whatever. Yeah, absolutely. So I could write that code to be like, well, if you've got a list and you got a list and you add them together, it's going to return a new list that's just both of them together. I could do that. I could write that. Because by default, C++ doesn't know what you want to add two lists together. It doesn't know what you want to add two arbitrary objects together, two arbitrary things. Addition is defined for a couple of types in C++, but then you can define what it means to add things. You can define what it means to divide, to subtract, to multiply, to compare. So the operator square brackets, that's saying like, okay, if someone uses the square brackets, that's what it's going to do. So that's what allows us to do this. Yeah?
So could you have used a different symbol other than square brackets, but just made it act in the same way?
Well, I think I know what you mean. Honestly, I've never tried that. I assume it would work. Like if I added two lists together, but that somehow just returned an index. Yeah, that would be. I suppose it might work if the types line up, but you shouldn't. Assuming I know what you mean. Other questions? So this is pretty cool. This is handy. So what do I have here? Add. Add element. Wait, why is this special? Didn't I do this already? Oh, right. Array ordered list. We're going back to array ordered list. I already ranted about this. Remember how, where'd you go? Where are you? You brought up that issue. The things are of type T. How do I know I can actually compare something of type, like I can actually ask, well, is this less than this? Well, it's this operator thing that allows us to be able to ask that question. If it's defined for those types, we're good to go. Pretty cool. So computational complexity, here's a quick quiz. What's the computational complexity if I have a list here? I guess this is an index list. What's the computational complexity of removing the first? 1. You're all wrong. Why? Because we have to shift everything down. 1. We need to shift, order it. Remove last. 1. Yeah, we don't need to shift. We're good. Remove something, some arbitrary thing. Why?
Search.
We have to search, we have to shift, we've got to, I mean, we might get lucky. That thing we might want to remove might be at the very end, but it might be at the very beginning. Or it might be the second last one, or it might be the second one. You know, on average, somewhere in the middle. We got to do a linear search. On average, who knows where it's going to be? It's going to be linear. I mean, maybe you could say like, well, it's like half of n. But what do we do with coefficients? Forget it. We need to shift things, order n. Sure, we might end up with everything. Oop. What's the computational complexity of just getting the first thing? How'd you know? Because I just showed you, yeah. What about the last thing? 1, because we know where it is. We just go right to it. We look it up. How about checking if something is contained within the list? Why?
Search.
Everyone, you gotta search for it. And if it's a linear search, it's a linear search. Yep. What about add something, add T?
Isn't it
I guess this is an add, I guess this is an ordered list. We're gonna have to do a linear search, shift the things. But what if this was the not linear search? What if this was the array, or pardon me, the index list? What would add be? 1, why?
Just add it to the end.
Because that add said just add something to the end. Sure, we may have had to have expanded capacity, but remember, amortization. Unordered lists, add to front.
And
Why? We got to shift. Unordered lists, add to rear. 1. Yep, cool. Unordered lists, add after.
and
1. And.
and
save the search for the big data.
All right, I got a lot of I got 2 answers. I need to come to consensus. Unordered list add after is.
and
Okay, good. Why?
You gotta find it.
We gotta find it, then we gotta shift things. Yeah. We might even have to expand capacity. Ooh. Index lists add. Why? We have to shift. We don't have to search because we're just going right to that index. We might have to expand capacity. Index lists add to the end. We just answered that. Index list set something at an index to an element.
1.
Who says 1? Who says n? Why? With set, we never had to shift. Ah, I gotcha. It's order 1, because with set, you're just going in and overriding whatever's in there. We don't have to shift anything. So we're good. Index list get something at a given index.
1.
It's not linear?
No.
Why not?
It has an index.
We're not removing anything, we don't have to search for anything, we just go right to that index. Index list, index of. Who said 1? Did you change it to n? So what is it?
We need to search for the n.
What did you say?
N.
Why?
We need to search for the element.
We gotta search for it, right. Index list remove something at a given index. Why? Shift. Index lists this operator thing. Yeah, we're just getting something. That's cool. So, you might be thinking, with all the, remember we had a whole bunch of add to fronts, remove from front? We could do that with some of those lists, right? Why not do this circular array idea that we did before? Wouldn't that actually kind of like save some time? Given the fact that we won't have to do those extra shifts, right? I mean, that's a good point. You're not wrong. But I suppose we need to really consider how often are we moving from the front and how often are we going to remove just not from the front? Is it worth it? Right? Because I'll only save time if I'm removing from the front. But let's say I remove the thing right after the front. I still have to shift like almost all n things. So is it really worth it? Maybe. But these are things to consider. Things to keep in the back of your mind. So we made an array list. Do you think we can make a linked list?
Yes.
Who says yeah? Who says no? Good, because of course we can. There's nothing stopping us. Now, we're not going to do it here, but you, by all means, can implement it. In fact, you will start to implement it in the lab on tomorrow or Friday. But things we need to remember. After this, okay, the following slides are taken directly from the nodes and links slides. I'm not showing you anything new. This is just things we need to remember when dealing with the link structures. Adding to the front. I want to add this node to the front such that that blue node is head. Talk amongst yourselves. I'm going to give you 30 seconds. Talk amongst yourselves and think of the steps that you need to do. What are the steps? Line by line code. Convince each other. Remember, order matters. All right, what is it? I want somebody new. I appreciate your enthusiasm. Who's going to tell me the code? What do you say?
Again, you add another pointer, say front or something, point that to yellow, have head point to blue, and have blue point to yellow, and then delete the excess pointers.
Well, we don't need to delete the pointers. The pointers, whatever, they don't matter. I mean, you're not wrong, but we can clean it up a little bit. I would just say, node, your next is head, and then head be equal to node. That's what I would do. That's what you were saying. You just create an extra pointer, which is fine. Nothing wrong with that. But I did one less line of code. So node, make your next head, and then head point to node. Great. Adding to the middle. Here's a node. Here's the list. Insert the new node after the third node in the linked structure. 1, 2, 3. So I guess after that, cyan one, whatever color that is. Turquoise? Sure. What would that code be? I'll give you a big hint. We might need another pointer. Don't want to say any more. It's too quiet. Is it because you don't know, or it's because this is so trivial for you? Do you have an answer or you just have questions? All right, we'll wait a second. All right. Raise your hand if you're like, yeah, I know. Really high, I want to see. Okay, that's very concerning because this is like a month and a half ago. Who here says it would be something like this? Current set next to node. Yeah? Yeah? If you just nodded your head, you're wrong. Why are you wrong?
You lose the next.
Oh, we lose reference to the next one. We need to be careful about the order here. Node set next to current's next. Then current set next to node. We need to be careful. So we need to say, node, your next is current's next. Right? Then current set your next to node. Now we're fine. If you do it in the wrong order, you're in big trouble. You suddenly lost reference to that list. For all you know, what if there's like 1 billion elements in that list? And you accidentally lost your reference to the head of that sublist? You're in big trouble. That's no good. So whoever nodded your head, get it together. Any questions? Okay. Adding to the end. Well, it's actually basically exactly the same. Deleting from the front. Oh yeah, good question.
So back at the other side, I raised my hand too late, sorry. Why couldn't you use something like index I instead of current?
Well, there is no such thing as an index here. This is a link structure. Arrays have indices. These series of nodes pointing to each other, there's no such thing as an index. I mean, if we created an index, if we created a linked indexed array, linked indexed list, then we could, if we were building it with that, but this is a link structure. There's no such thing. You can't index this link structure. You can only iterate through it with like next, 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 and whatnot. And checking if pointers are null. Deleting from the front. How would I do this? Head equals heads, get next. All right, cool. That was kind of easy. Deleting from the middle. I want to delete this turquoise one. What do I do?
Temp is equal to the
Don't tell me, tell each other. Yeah, we want to get the teal, cyan, turquoise, whatever color that is. Bluish, greenish. Yeah, that one. The one being pointed at. All right, it's quiet, so I assume everyone's got the answer. Raise your hand if you're like, yeah, I know. Really high, I want to see. Really, really high. Let's see, who am I gonna get? Okay, what do you say? Back left. You just had your hand up.
I don't know how to word it.
Okay, let's see. Okay, raise your, everyone put your hand back up. What do you say?
Set the dark blue,
Whoa, hold on. I can't just set the dark blue.
or have the dark blue point to the black, I mean.
That's what we want to have happen. But how do we do it?
Have it point to currents next.
But hold on. I'm being difficult, right? Of course, what you are explaining is the correct answer. But you're saying, oh, set the dark blues next to black, next to like currents next. But how do I get to the dark blue? I only have a pointer to current. What do you say?
Would it be like currents former or current -1?
Well, you see, what you want to do is correct, but how you're doing it is not correct. What do you say?
You iterate through it until the next is current.
Okay, just let me clarify. Somehow we gotta get to this.
Yeah.
And how do we do it? We start at the beginning, and we keep checking, is your next, well, excluding edge cases about like the front, is your next current? If it is, I found the spot. If it's not, keep going. So I would start at light blue, gray, whatever color that is, and then say, okay, is my next current?
No.
No. Okay, go to the next one. Is the next current?
No.
No. Now I'm at the dark blue one. Is the next current? Yes. I stop. I'm where I need to be. Then what do I do?
Then you set it to, you point it to the black square.
Whoa, how do I do that?
Use currents get next.
Okay, so currents get next gives me a pointer to the black square. So I've got a pointer to the black square. Now what?
And then you delete the current.
Yeah, but we're missing one critical step. This,
Set it back to previous.
well, put up your hand so I can point at you.
Set it back to previous.
Set previous next to currents next. Or alternatively, previous next to previous next or something. Then delete
Correct.
current. There we go. We did it. This is good. Like, by the way, depending on how you're doing your assignment 2, or assignment 3, this could be critically important for you. So yeah, there we go. So, okay, deleting from the middle, awesome. Deleting from the end, basically the same as before. So our linked implementation would look something like this, probably. I'm trying to think for a second. Imagine we have our linked implementation. And I say I've got this linked implementation and I have an indexed list. And it's a linked implementation. If I said set something at location I, what would the complexity of that be? 1. Why?
You have the index to it.
I don't. I could just jump to the arrays index, because when it was an array implementation, everything was in an array, and the array had indices. And if I were to say, oh, go set something at index I to something, all right, I would just go to the array at that index and change it. I could just jump to an index immediately. But when I have a link structure, remember, I want the link structure to pretend it's indexable. But the underlying link structure is not indexable. It's the class that we're writing that's going to make it seem as if it is. So what's the complexity actually? N. Why?
We need to search.
Because I'm going to have to start at the front, and if I want index 4, I'm going to have to go next, and so on. If I want index n, I'm going to have to do next, until I get to it. Ugh. I mean, but at the same time, remember with the array implementation, what was the complexity of adding something to the front? What about removing something from the front? With the linked implementation, what's the complexity of adding something to the front? 1. How about removing? 1. We have those trade-offs. Sometimes you win, sometimes you lose. What's better? It's up to you. Depends on how you're using it. I don't know. I couldn't tell you what to use. There's no silver bullet. Although in practice, use the array ones because they're faster. But that's just a consequence of how those box computers that you're using work. Remember, these algorithms, we're writing them for the computer, but any computational system could execute it. So it doesn't really matter, I suppose. Any last questions about the lists? Yeah?
So, like, what really makes like a linked implementation like a list? Is it the way that the user would like interact with it? Like
Exactly. It's the linked structure is going to be within the class, one of the list classes. And the way I interact with the list class, because I'm not ever actually directly if I have a list class and I create a linked list of some sort, I'm never going to directly interact with the underlying linked structure. I have to communicate with that underlying linked structure through that class, the list class. And that list class is going to make it seem as if like, oh, I can do whatever, I can add, I can remove. But that class is going to do all that lifting for me. All I have to say is, oh, set. How did set work? I don't know, it doesn't matter. All I know is that it worked. How does get work? I don't know, it doesn't matter. All I know is that it works and I'm happy. So it's the class. I'm looking at it through the lens of that class, and suddenly, oh, it's a list. Even though really it's just a link structure.
so it's a list.
It's a list, just like the array. The array is not a list. The array can't arbitrarily get larger. The list can. Why? Well, because that list hit all that work for me. It expanded capacity whenever it needed to. I don't care. It doesn't matter to me. Did you ever have to expand the capacity of your lists in Python? No. Do you even know how the lists in Python worked? No. Does that matter? No, not really. You can still use it. Did knowing how it worked or not worked affect how you did assignment 1, 2, 3, or 4? No. So it's that lens. It's that like middleman, basically. Other questions? Cool. I'm going to blitz through this one just to show you something. This is not going to be overly critical that you really know it, but I'm going to show it to you because it's interesting nonetheless. So we actually have these things called structures, which is a way to basically group simple things together. Simple, like pieces of information together. It's basically like a super simple class. It's a dumbed down class that just and it just has like attributes. So here, if I put this in my code, I have defined what we call a structure. Now this is like the general case, but here's an example. I can create a person structure, and that person has 3 values associated with it. A first name, which is a string, a last name, which is a string, and an integer, which is an age. Why? Well, because I just arbitrarily picked them. Whatever's in there doesn't really matter. So this is kind of like defining a super watered down version of a class. There's no methods here. It's only kind of like we have attributes. So if I make one, I could write it like this. And that's the syntax to create one. I'm creating a person, its variable name is A, and then blah, blah, blah. Order matters here. The first attribute will be the first thing we put in there, then the next one, then the next one. So in this case, what's the person's age? How'd you know? Because it's the third one, and also it's the only integer, so that's probably what it was. And if you want to get the attributes, it's just like that. A, F name. A, last name. Pretty easy. In fact, this code would be very similar if we made the attributes, it would actually be like identical. If we made the attributes of a class public. That's how we would access them. So it's actually kind of neat. Here's another way of creating one. I'm going to do one like this. Just create one, but don't set anything, and then go inside and then set the values later. So not only can I access the things by saying like b.fname, I can set them by saying b.fname equals Jane, there. Here's another example of making one. I could do it with a pointer. Why? Well, because I want it. Free to do it. There. And we would use it this way. This should look pretty darn similar to what you were used to with dealing with classes. Is it the object or is it pointed to the object? I could have done this with dereferencing, but I use that little like arrow thing. Yeah?
Is it the same as with a class, like it needs to be in a different file and you import it?
No, these don't. Structures and structures. I could have one of the values inside a structure be another structure. And here I made it a person pointer. And person was a structure. So my structure address has a pointer to a person, a street address, city code, substate, country, whatever. And I could do this. Pointer to A, 123 Nowhere Road, Enniganish, whatever, whatever. Why did I make those strings and that a pointer to a person? Because I wanted. The values I put in there and their types are arbitrary. I'm just showing you how you might be able to use this. Pretty cool. Now, for those of you that took engineering last semester, did you learn about structures? Yeah. Yes? No? All right, well that's interesting. Some of you, did you take it last year? Did you take it 2 years ago? Okay, well that might explain it. Okay. And anyways, yeah, there we go. Structures with parameters, just like anything, you can pass them as parameters. Cool. So here's another weird one. If you look at this and you think, great, you never use it for the rest of your life, that's fine. It doesn't matter. But it's cool nonetheless. Sometimes we want like a new type for integer constants, right? So I could create a constant for, remember with constants, a good use of a constant could be, remember in my find method in the previous slides? Find. It returned the index of where the thing was, or -1 if it didn't exist. But what I could have done is I could have made a constant that was like not found, like not underscore found, and set it to like -1. And then I could check like, oh, did it return not found? It's still only really comparing -1 to -1, but that label for the constant is a good idea. Because if you're a programmer and you look at the -1 being returned whenever someone calls found, you might say, well, what the hell does -1 mean? But if I put that constant in that said not found, and I wrote the code, you didn't, but I give it to you, you would immediately look at that code and be like, oh, it's a special value for, oh, it wasn't found. So constants are handy. But sometimes we want constants, and sometimes there might be some sort of ordering that belongs to the constants as well. This is best explained with an example. So I can do something like this. Monday, Tuesday, Wednesday, Thursday, Friday, the days of the work week. So right now, it's kind of like I'm creating a constant for Monday, which would be 0. Tuesday's 1. Wednesday's 3, and so on. That's what this code does. Like that. Now the reason, like here's an example of it being used. It's kind of clever. So I set a day. No, it's not an int, it's a day. And I'm setting the day to Tuesday. Checks out. But what does Tuesday really mean? 1. But if I'm a programmer, I'm like, oh, it's a day, it's Tuesday. It's more meaningful to me. The code's more handy. It doesn't really affect how it runs, it affects how I interpret that code. And now I can do something like this. Start at Monday, loop to Friday, add 1 to the day, print it out. I can even check if the day is equal to Tuesday. Not equal to 1. If it's equal, is like day equal Tuesday. And it would work. Pretty neat. So what's the point? Well, maybe I can do something like this. Int day, Monday to Friday, print out the daily sales. If the day's Tuesday, like I just said, I decide I'm going to add out an extra thing like, oh, expected high sales on Tuesday. Why? I don't know why. But let's say I just want to do that. So now it gives me a way to do this, and this code becomes a little bit more interpretable, which is a good thing. We like our code to be descriptive. And that's that. Any questions about that? Yes?
Can you do that with user input?
With user input?
Yeah.
I'm not sure what you mean.
Like have a user type in the date and then use that for the rest of the code? Like how you get them to
Well,
put it in.
that would kind of defeat the point of like the constant stuff, but you could use a very similar idea. Yeah. Yeah.
So do structures not work in a way of like sets?
Say that again.
Could you think of a structure as like a set almost?
I'd be careful to say that. I'd be careful to create a generalization like that.
Just because when you look at it, it's like a loose connection of like data together. It doesn't have to be the same type, and it's very like not super strict almost.
Yeah, let's not worry about that too much. Because sets, we would typically define set as its own class.
Yeah.